Hi there and welcome to this lecture on eruptive styles. In this lecture we're going to take a specific look at how magma comes out of the Earth's surface. Believe it or not, there are many different ways in which this happens, and mostly it's controlled by the viscosity of the magma. So we'll take a look first at what viscosity is and how it affects magma, and then we'll take a look at the styles themselves and relate it to what we've learned about viscosity. So with that being said, let's go ahead and get started. Let's go to the next slide. So silica content and explosivity go hand in hand with one another, and I want you to keep that in the back of your mind as we go through these slides. You'll notice on that arrow it says low, medium, and high, and that's referring to both silica content and explosivity. On the top of the arrow you see the different kind of volcano constructs you can get related to the different silica content and explosivity. In a separate lecture segment we'll take a look at those constructs in more detail. In this lecture we're going to take a look at these styles, which are Hawaiian eruptions, Strombolian eruptions, Vulcanian eruptions, Plinian eruptions, and super eruptions. And you can see just by the photos as you go up that they do get more and more explosive in nature. And we'll take a look at why that happens. There's no photo for super eruptions. We have not had one in historic time. Thank goodness, right? So hopefully we don't have a picture of that anytime soon, but we'll still learn about those as well because they have happened in the geologic past, so we'll take a look at that closely too. All right, so with that being said, let's take a look at viscosity and how that plays a role. So viscosity is defined as the resistance to flow. High viscosity means high resistance to flow, which simply means that the fluid is resisting movement. So it would have a slower movement associated with it. Low viscosity means low resistance to flow, which means that the fluid isn't resisting flow and can actually flow very quickly as a result. It's really helpful to remember that viscosity means resistance to flow, so that you can actually relate that to whether you have high viscosity or low viscosity. If you can memorize resistance to flow as a definition of viscosity, just adding high or low to that definition then will easily tell you what kind of fluid you're looking at. So I also ask that you don't think of viscosity as thickness. In the sciences, we don't consider viscosity having anything to do with thickness. Thickness is a measurement that has nothing to do with fluid flow. We talk about viscosity relating to a resistance to flow, and that's it. So I don't want to see on your activities any kind of reference to thickness. I'll know what you mean, but in the sciences, since we don't refer to it that way, I would ask that you don't refer to it that way in this class as well. All right, so with that being said, let's take a look at how magma is affected by this viscosity. What makes magma change its viscosity? There's actually three reasons. A lot of you probably already understand that temperature plays a big role. For example, if you have pancake syrup in the fridge and you pull it out and you try to pour it on your pancakes right away, you know that that pancake syrup isn't going to come out as easily as if you took that syrup, put it in a microwave, and then poured it on your pancakes. You know, heating up the syrup is allowing for it to be more fluid and have a low resistance to flow, which means a low viscosity. Magma is exactly the same way, and any substance actually is. The higher the temperature of the magma, the less resistant to flow it is, which means it has a low viscosity. Cooler the magma is, the higher its viscosity, or the higher its resistance to flow will be. That has everything to do with how the volcano itself is shaped, which we'll spend some time on in the next segment of this lecture. Composition plays a role because of the silicate structure within the magma. If it's got a high silica content, it's got the silicon oxygen tetrahedron in it like every magma does, but that tetrahedron structure is going to be more complex. In the higher silica content, it's actually forming itself into sheets and 3D networks, and that actually makes the fluid more resistant to flow when you've got those more complex structures in there. If you have a low silica content, that means you've got more of a single tetrahedron structure in the magma, maybe single or double chains, and the magma is actually going to be more fluid as a result because it's not as complex. The fluid can flow more freely in a less complex molecular situation. So the composition by itself is playing a role in viscosity. Dissolved gases play a role as well, in particular water vapor and also carbon dioxide as well, even though I didn't really put it in the slide here. It actually makes the magma a bit more sticky, and so if you're making the molecules kind of stick together, that's going to make the flow more hindered, so get more viscosity that way, a higher viscosity that way, more resistance to flow. So if there's less water vapor in the magma, it can flow much more freely as a result. All right, so those are the three things that affect a magma's viscosity. Let's go ahead now and take a look at the different kinds of eruptions that stem from this. Let's go to the next slide. So the first thing we have is Hawaiian eruptions. I'll preface that by saying, before we get into the details, that Hawaiian eruptions can happen anywhere in the world. It doesn't have to be in Hawaii, although you could see by the name that it probably does happen in Hawaii, and in fact that's where these eruptions were first documented and classified. But it's important to realize that all volcanoes, most volcanoes that we're going to talk about actually, can have a Hawaiian eruption event anywhere in the world. The lava is of low viscosity. Its composition is therefore going to be mafic. Its temperature is going to be relatively hot, and the volatile content relatively low. So that's going to all equate to a very calm, non-explosive event. The reason for that is the magma is very buoyant. It's very hot, so it's going to be very buoyant, and it's going to be able to escape through any little crack very easily because of its low viscosity and the fact that it just wants to rise buoyantly because it's so hot. So it actually is our most common rock type on the planet. It makes up all of the ocean floor, and also makes up what are called shield volcanoes, which the Hawaiian Islands, by the way, are mostly made up of shield volcanoes. And we have several shield volcanoes on continents as well across the world. But all of that is, basically Hawaiian eruptions are the most common just because this magma can easily escape. Out of all the different kinds of magmas, the mafic magmas have the easiest time of making it to the Earth's surface because of how they are with what we just talked about. All right, I want you to take a look at two different types of Hawaiian flows. There's two distinctive types. There are what are called a'a flows, and there are what are called hoi flows, and they all are mafic. They're all very low viscosity, but because of their slight difference in that low viscosity zone, they have different appearances. So the a'a flow is this flow right here. It looks very blocky, and in fact it means blocky. A'a. In fact, by the way, a'a is a word. So if you do play Scrabble, you need to get rid of some A's. This counts, definitely. Aside from that, it is got a higher viscosity. Now I want to make sure you understand that I'm not saying it has a high viscosity. I'm saying it has a slightly higher viscosity than the hoi flow, and there's a difference there. It's still a very fluid magma. So overall, if you were to point at an a'a flow, what you would tell me is, oh, that's a low viscosity flow. But what you would also tell me, but it's slightly higher than a hoi flow as far as viscosity is concerned. There's a distinction there. So don't come back and tell me a'a flows are high viscosity and hoi flows are low viscosity, or you'll be marked wrong if you have to answer that in any questions. You just want to tell me, no, that's a low viscosity flow. It just has a slightly higher viscosity than the hoi flow. And then you'll have the exact understanding that you need for this particular section. All right, you'll notice that the Pohohoi flow is very ropey. It was a picture in the previous slide. It's just a flow that's flowing very freely and easily, and when it solidifies, it looks very ropey as a result. So it has a much different look. And if you walk across Hawaii lava flows after they've solidified and turned into basalt, you'll know the reason why you're seeing the different characteristics that you're seeing, and you'll see these distinctively there. It's not something, oh, I think that might be but it might be Pohohoi. No, they are very distinctive from one another, and you'll have a little bit more knowledge than the tourists that would be next to you might have. All right, let's go ahead and go to the next slide now and talk about the next explosive type. So strombolian eruptions are the type of eruptions that are also of low viscosity. The magma is able to escape out pretty easily, so there's not a lot of pressure buildup with these type of eruptions. However, there's enough of a pressure buildup where when it does come out, it kind of fountains a little bit. If you're standing next to a strombolian eruption by itself without anything else to compare it to, you might call that explosive. You might say, oh, that's really explosive because it's kind of startling and it's magma spraying up and it's not something you would normally see, and it would maybe prompt you to say that's explosive. But if you stood next to a strombolian eruption and placed it next to something like a Vulcanian or a Plinian eruption, they're night and day different. So when I say that this is still kind of a mildly explosive event, I'm comparing to something that's much larger that could occur in a volcano. This kind of eruption just fountains and spatters, and it creates cinders. Basically, those little blobs of magma that are flying through the air solidify midair and land and pile up and create what's called a cinder cone. So we'll talk about cinder cones in the next segment of this lecture. They are also always mafic. These eruptions don't happen with any other kind of composition material. Let's go ahead now and take a look at a picture showing that spring in just a little better visual detail there than the other picture. So you can see the fountain there, and you can see in the air it looks kind of like some ash, which there's ash coming out of there a little bit. But there's also, you can see black dots, and that's the cinders. That's the magma that's solidified in midair, and it's going to land and pile up right there. And there's some lava flows coming out of this as well right through there. That's where the ash and steam is coming out of, or coming from, I should say. All right, let's go to the next slide and take a look at the next explosive type of event, and that's a Vulcanian eruption. These are associated more with intermediate composition type of volcanism. We'll learn about stratovolcanoes in the next segment, and this is the type of eruption that can occur out of those volcanoes. They're categorized as having ash clouds and pyroclastic flows as part of their process. Ash clouds, you can see there, just made of little pieces of glass that are light enough to be pushed out of the volcano and float in midair for quite a while before they land somewhere either near the volcano, or winds may blow that away from the volcano at some distance. They're moderately explosive and a lot more scary if you're standing next to it than a strombolian eruption by far. This particular cloud will reach up to 10 kilometers in height. If it gets much higher, we actually will classify it as a Plinian eruption. And we'll talk about that in just a moment. But before I do, I want to talk about what pyroclastic flows are in a little bit more detail. Let's go to the next slide. So that's a picture of pyroclastic flow. It's basically a mix of ash and boulders and debris coming down the side of a volcano. And if you're hit by that, of course, you could get killed by the debris that's coming down the side of the mountain. But what you'd probably get killed by more is you'd probably be incinerated, because these clouds are very hot. They're upwards of several hundred degrees Celsius coming down that mountain. So you basically be incinerated if you get hit by one. It's just a very dangerous type of event, and if you're a volcanologist studying volcanoes, one of the greatest leading causes of death from this particular occupation is getting hit by a pyroclastic flow, unfortunately. Let's take a look at this particular flow after the ash has settled, so to speak. Let's go to the next slide. So this is from the same particular eruption sequence there, and this is actually what the eruption left behind. The pyroclastic flow came from over here, flowed down this direction, and you can actually see from the force of the flow, it actually indentated this gravel a bit. But as it lost its energy, all the big stuff it was carrying were deposited in that pile that you see there. It's deposited in a pile because that's basically where, again, the pyroclastic flow lost its energy, and so things will settle out at that point. And so that geologist there is actually cataloging and categorizing the different size of the clasts to get at how much energy was within that flow at the time it was happening, because the size of the grains will actually give you that information. All right, so here is another photo, a much more scarier photo of Mount Pinatubo in 1991. I think I showed you this in a previous segment of this lecture, but this is an example of a pyroclastic flow, and they move at 100 miles per hour sometimes across the surface, sometimes a little bit faster. So it's very hard to outrun, especially if you're on a dirt road. And as I mentioned before, this person was getting rescued. The person who took the photo was in a helicopter waiting for these people to reach them so they could fly to safety. And of course they did get out okay, because the photo did make it. So the camera would not have survived that particular event if they did not make it. But just incredible footage that is very rare. We don't get those kind of vantage points photo-wise of pyroclastic flows. So it's a very famous photo in the scientific community as well as just in general. Let's go to the next slide now, and the Plinian eruption is the most violent as far as common eruptions are concerned, at least eruptions that have happened within our historic time. They are associated with a higher viscosity magma, and that's because the higher the viscosity of the magma, obviously the higher silica content there is. And something that I haven't mentioned is that silica content, when the molecules become more complex, they also become stronger. And so when you have the volcano capped with high viscosity, high silica content rock, the magma underneath starts to build up, and the gases within it start to create more pressure. And that pressure has to super exceed the strength of those very strong silicate rocks that cap these kind of volcanoes. And so once that happens, that's not going to happen in a very mild sort of way. It's going to happen in a very explosive sort of way. And this particular photo actually is of Mount Lassen, which is in Northern California, and probably the closest, it is the closest stratovolcano related to subduction to us here in the Bay Area. And this photo was taken in May 22nd, 1915. And this volcano had a sequence of eruptions that lasted 3 years, up to I think 1918, I believe. I'm doing that by memory. I could be off just a little bit on the year there, but this was taken in Anderson, California, which is about where Interstate 5 is in relation to where this volcano is at. So just an incredible ash cloud. This ash cloud reaches up to and sometimes higher than 20 kilometers in height. So it's very similar to how a thunderstorm might develop. And you can see the big thunderstorm clouds with the billowing tower and anvil-shaped head and all that. These ash clouds look very similar in shape to that because they're really going up to the same heights as these thunderstorms do. All right, so something else that you can get out of these very violent eruptions like Plinian eruptions and Vulcanian eruptions is something called a lahar, or what is also known as a mud flow. And this is particularly dangerous when there's heavy rains going on at the same time as the eruption, or if the volcano is ice capped and the ice cap melts very rapidly. This is a danger that Mount Rainier in Washington State can certainly pose on the residents around that volcano. and in fact this has happened in the geologic past with this volcano, because we see the deposition left behind from the ancient mud flows that Mount Rainier has done. So you can see in the photo just how thick this mud is if you look at the roof lines of the houses and then take a look at where the mud is sitting, and just incredibly messy. It's hard to clean up. In fact, a lot of areas won't clean it up. They just kind of move on and rebuild somewhere else, just because of the nature of this. It's just really a lot of material. And again, it's just a mixture of water and debris from the volcano, whether it be ash or dirt or soil or whatever the volcano can pick up along the way as it goes down and out from the vent. All right, so the last kind of eruption I want to talk about are the dome building eruptions. After the Plinian eruption happens out of these stratovolcanoes that we'll talk about in the next segment, they kind of rebuild their cone shape. You'll notice Mount St. Helens, if you look at that, if you get a chance to go visit it, or if you look at photos of it, its top blew off. And over the series of next couple hundred years, that volcano is going to rebuild its cone, and that happens through these dome-building eruptions that are very, very viscous, high viscosity, kind of like toothpaste coming out of a toothpaste container. Here's an example of a dome-building eruption that happened only a couple years ago out of Mount St. Helens. So it's continuously doing this. You'll notice that the magma is very light colored. It's not dark like some of the photos you've seen of the Hawaiian flows. That's because of its high silica content, mostly pink and light colors. And it usually follows, again, a violent eruption. Let's go to the next slide. This is a picture of Mount St. Helens just after the 1980 eruption, and there's a dome that started to already build up soon after the big eruption took place. And if you look closer, this is actually a dome that was built only a couple years ago within that zone that was vacated. So that dome right there is all really viscous, rhyolitic type of lava there. And the white is water vapor. If a volcano is shooting out white, basically white, what looks like clouds, that's actually water vapor, not ash. If it's gray, it's ash. If it's white, it's just water, condensed water vapor, basically. I shouldn't say it's water vapor because it actually isn't. Water vapor is coming out, and then as soon as it hits the atmosphere, it condenses to water droplets. So we call it condensed at that point. And there's another picture of the rhyolitic flow. Just very, very viscous in nature. All right, so that's the end of this segment. In the next one, you'll learn about the volcanic constructs, and we'll talk more about not only the stratovolcanoes and the shield volcanoes and the cinder cones. We'll also take a closer look at the supervolcanoes as well. And thank you very much, and I will see you in the next lecture.